Hello everybody, my name is Tassos and I'm with RF Elements, and today we'll be doing our Increasing Throughput 101 webinar. This webinar will be helping you to, again, just increase the throughput of your networks based on the utilization of our antenna technology. So if we look at one of the challenges of being a WISP, the challenge is really keeping up with the demand for throughput. This has changed a couple of different ways. Not only is the demand for the number of internet connections growing almost exponentially, right? The number of people who require internet connectivity. We also have on top of that the growth in demand for the speed of those connections. So it becomes very challenging to not only keep up with the demand in number of connections, but it's also increasing the speed of each of those connections that have become one of the major challenges for WISPs. If we look at the challenge in trying to meet that demand, right, really there's a challenge of dealing with the lack of spectrum. Spectrum is really the Achilles heel here, and what we have to address in order to, again, really compete in this WISP market. And to cover this growing demand, new standards have been introduced with new radio platforms that have higher theoretical speeds, more complex modulation rates, and really, when it comes down to it, they really need to focus on spectral efficiency. So these new higher speeds and more complex modulation rates all require more spectrum to do it, right? And we know that spectrum is limited, right? Not only do we have the limitation of the channels that are available to us, when we compound on top of that all the RF interference that we have, it makes it very difficult to even be able to utilize all the channels that we have available to us. And most wireless vendors have tried to kind of address this issue by bringing, these newer advanced technologies, like complex solutions like TDMA, active filtering, and GPS synchronization, right? These new technologies by themselves are really not sufficient for dealing with the issues of spectrum. And the problem is really, again, noise, RF noise. So, vendors are not solving the problem at its roots. Rather they're dealing with the consequences of what's there, and it's really the wrong approach. We really need to look at the root cause, which is noise, and trying to reduce noise and reject noise. So therefore, our radios have a better ability of coexisting in this really dynamic RF environment that we see today. If we look at some of the solutions, for interference, one of the main ones is shield kits, right? We see this all the time. People are buying antennas that aren't performing, so you go ahead and you spend even more money on these aftermarket shield kits to try and fix your problem for noise. And really, all this is doing is just, moving the problem somewhere else, right? So, these shielding kits kind of help with the near field radiation and colocation, but it's not dealing with the issue of noise itself, right? It's really not the best approach for trying to, again, navigate the spectrum that you have and getting your connections to be fast, right? Because what these shield kits end up doing is, giving you the kind of false hope that things are better by, again, shielding your colocation of sectors on a tower, making it seem like things are going better. But in the end, what they do is they warp the main signal that comes out of your antenna that serves your customers. So it may give you better colocation at the tower, but it's translating to lower modulation rates at the customer. So really, it's not the solution for the problem. If we look at the radio platform vendors again, right, we can see kind of where we've gone from 802.11n, the first step in increasing speed by higher modulation rates and more efficient protocols. And then we look at things like GPS synchronization, right, the ability to utilize the same channel and therefore, allow you to use less channels on your tower. And then if we go into the AC world, again, we're going into much wider channels to try and deliver more bandwidth by having higher modulation rates. And then you couple that with GPS synchronization and you put active filtering on top of that. All of this, again, is trying to combat the problem of noise, but none of these actually help address and fix the issue of noise. So at RF Elements, we deal with the problem at the source, and we do it through two main methods: creating antennas that reject noise by having no side lobes, and having a ecosystem of twist port adapters that are vendor neutral and bring you near zero loss from the radio to your actual antenna. And this is again, through two different products that we have: our symmetrical horn antennas and our twist port adapters for our twist port ecosystem. When you utilize both of these technologies, you start seeing great improvements in how your radios work, more efficient radios, and therefore really addressing the issue of noise, not just by rejecting it, but also making sure that we don't create any noise and we reduce as much loss as possible. So if we look at noise rejection and where we're kind of going with this, the biggest part about dealing with noise is trying to create an antenna or utilizing an antenna that has no side lobes. And people ask, well, what does side lobes mean and why is that important? So if we look at this animation here, you can see this is the kind of typical coverage pattern, right, or a 2D, two-dimensional polar plot on the left that you would see of your traditional 90 or 120 degree sector antenna. These are your traditional sector antennas. If you look at the part in the red on the bottom, these are what are called side lobes, right? These are secondary and third type nodules that come out from the antenna that are actually very effective secondary antennas, if you want to look at it from that point. And typically the side lobes are not coming out in the main direction that you want to service. So therefore they're hearing noise from behind and from the side of the sector. These are areas where your radio should not be listening to because it's not part of your coverage area. If we look on the right-hand side, we can look at the dB relationship to these side lobes, and we can see, even though they're not as intense, they don't have the high gain of the main lobe, they still have quite high gain, sometimes as high as 10 or 11 dB, which is again a very high dB rating for a side lobe that helps increase your noise reception, which is bad, but also high enough gain that it helps create noise by sending signal in directions where you don't want them to go, right? And you may not care because it's not going towards the customers that you're trying to service, but it's going in directions where you have other customers that you might be servicing with other towers and other APs, and this is how we create these problems. If we look at a horn antenna pattern, you can see it's nothing but main beam connectivity. You have nothing but the front facing 30, 40, 50, 60, 90 degree antenna pattern that you've actually purchased. So the antennas have great noise isolation because they don't hear from the back with secondary lobes like traditional sectors, and therefore you get good noise rejection because it hears less spectrum, and also it's great at decreasing noise because it's not, again, transmitting in directions that you don't want them to go into. The same can be said for point-to-point antennas, right? So point-to-point antennas are actually one of the most misunderstood RF antennas because people are often fixated on that main beam, that main lobe, that 3 degree, 8 degree, 10 degree main beam of an antenna, right? And nobody really pays attention to the intensity and the complexity of the side lobes from these antennas. So if we look at the areas in red, we could see even on a point-to-point that the side lobes have enough magnitude to potentially touch or create an issue for other co-located backhauls on other towers, right? So again, these side lobes are even more intense than sectors, because as you increase the main gain of an antenna, you also increase the magnitude of the side lobes. So your typical point-to-point parabolic dish antenna is usually about 28 dB, right? So that's about 10 dB more than your kind of standard 19 to 20 dB sector. And what that translates to is potentially another 5 dB of gain on the side lobe. So you can start seeing, as you use higher and higher gain antennas, the side lobes grow in that same proportion, right? So they become even more difficult to deal with. They send, again, higher magnitude signals out in unwanted directions, and they hear signals from unwanted directions as well. If we look at the same type of point-to-point antenna system built on horn antenna technology, again, you can see the absence of side lobes really creates this better environment where you're not, again, fighting with colocation issues on the tower itself through side lobe interaction for all your APs and all your backhaul radios, but also further out in the field, right? The absence of those side lobes drastically reduces or almost eliminates the amount of noise that goes out, again, in other directions, not the main direction in which you want your antenna to transmit in. So that's noise rejection. If we look at zero loss, right? So if you look at your standard kind of antenna radio system, you have a radio with some pigtails that, you know, interface into an antenna, and those pigtails are a source of loss, right? So with a twist port adapter, we're able to control the loss, right? We are able to get the radio to be more efficient in transmitting the power from the radio to the antenna with much less loss than external pigtails. And on top of that, you also reduce one of the highest failure modes for outdoor antenna systems, which is water ingress into those unprotected pigtails, even if you use mastic and tape in order to try and seal those antennas, seal those connectors. So if we want to compare a patch array sector, your traditional sector, to a horn antenna, you can see here, this is your typical traditional sector antenna, okay? If we look at the MIMO world, we usually have two different poles. We have a horizontal and a vertical polarization, right? In patch array sectors, typically they're not matched, right? So your vertical will have a wider or narrower than your horizontal beam will have, and this causes issues. On top of that, patch array sector, traditional sectors have, again, huge side lobes. This is your huge noise receptor. When we go beyond that, we even look at low performance areas. This is areas where the sector is actually much wider than you assume it is, right? So if we look at the customer distribution beyond or throughout that coverage area, usually there's a sweet spot. The green guys in the middle are usually the ones that get the highest MCS rates. And as you start moving out towards the edge of the sector, performance starts to degrade until you actually get to the edge of sector where it's really poor. If we look at a horn antenna, one of the big drastic differences is that the vertical and horizontal beam are practically identical. So you always have good MCS or good chain-to-chain performance, and all your customers distributed within that beam pattern have great signal because they're getting the high performance part of both vertical and horizontal chains, and therefore are able to maintain higher MCS levels and get much better speeds by not having a high diversity of MCS rates throughout the coverage area. So a horn antenna gives you excellent throughput, and we say a sector antenna gives you somewhat mediocre throughput because of the existence of such poor performing aspects of that RF coverage pattern. So let's look at noise rejection and how this actually happens kind of in the field, right? So if we look at, again, a standard kind of deployment, you have your AP and you have your traditional sector, right? So you have this coverage area where all your customers are, and when noise is introduced, either being received through the side lobes or through the low performance section of your antenna, throughput is reduced, right? Where with a horn antenna, there is very little noise reception through side lobes, and the actual coverage area is very defined and very precise, right? So you're only hearing, the spectrum that you care about servicing, and really does a great job of ignoring everything but that. So that helps increase your speeds because you can have better MCS rates to your customer. So if we look at colocation of sectors and how this all comes together, again, you take your same coverage area, and again, you deploy a standard traditional sector. Again, your coverage area could be somewhat, or the speeds that are delivered are not so great because the area that it's covering, it has a diverse spread of customers throughout it, where with horn antennas, you have a high colocation capability, so you can actually segment out groups of customers, therefore reducing the number of connections per AP, giving them good chain-to-chain performance, high MCS rates, and therefore delivering higher throughput packages because you can increase the density of APs per area, where with traditional sectors it becomes very difficult to do, not only because of their size, but also physically because of how that type of antenna technology works. So if we look at, again, the old way versus the RF Elements way, we can see with traditional sectors, link performance is usually quite low because there's a high probability of receiving noise through side lobes. There's also a higher probability of receiving noise through the antenna pattern, which is much wider than the spec sheet says, where with RF Elements horns, again, you can utilize much more narrower coverage patterns that are extremely precise. They have extremely precise gain across the entire spectrum, and therefore give you the maximum noise rejection with the highest MCS rates and the most possible throughput than traditional sectors on the market today. So one of the points that usually comes up when we talk about increasing AP density and dealing with adding more access points, within a certain coverage area. So for example, taking a 90-degree sector, which used to have one AP and utilize one channel, and segmenting that into 3 different APs using 3 different channels. People say, well, I don't have 3 channels, I only have 1, right? And it really only seems that way because of the antenna you're using. So if we look at your first AP, you fire it up, and we look at a spectrum scan and say, okay, there's only something on 5700, so I have 5500 available and 5900 available, right? So then a competing WISP comes in, or maybe you have other towers where you fire up 2 more APs, and now those channels that look like they were available aren't, because your antenna is so wide it can hear both those APs. When you use a horn antenna instead, because it has no side lobes, that secondary channel 5500 and that other channel 5900 now become usable because it has no side lobes. It's rejecting the noise and it's rejecting the signal from those other APs, and therefore you actually have more channels available than you think. You just have to look at your spectrum through a horn antenna in order to see that, and not through a traditional sector. So that's one of the biggest misunderstandings about channel availability, or the thought that channels aren't there when they actually are. The same can be said for noise floor, right? So you may not have competing signals coming into your area for services, right? But if you have your AP covering your area, again, you look at the noise floor, it looks like, again, 5500 and 5900 are available. So let's say you have 2 more APs that fire up that aren't servicing that area, but the side lobes are large enough that they're coming into your area and your main AP can hear them. It's going to show up as an unusable channel, where again, if you use a horn antenna that has no side lobes and great noise rejection, you can see how the noise floor, or you can see how a potential channel that looked slightly usable now becomes highly usable, right? So again, it's not until you use an antenna that's designed properly and made to reject noise by not having side lobes that you really start to look at your spectrum in a different way, right? It really requires a whole new approach and a whole new way of looking at things in order to see what the benefits are and help increasing your throughput. So all this comes together for massive scalability. Oh, sorry. It's this massive scalability that we actually need, right? So, you know, again, if you're using traditional sectors, then you have a problem with noise because of side lobes, and it makes it very difficult to grow and add AP density to your existing towers, to other towers, and you know what have you. Again, because of the noise reception. With horn antennas, you can get that massive scalability. You have the ability to kind of utilize channels that weren't available before. You have the ability to increase your AP density and stuff like that in order to deliver more throughput packages to customers. And it's not until you migrate your network to nothing but horn antennas where you can really start to see the benefits of delivering high throughput packages to a high number of connections and you know, have a massive network and the networks that we need these days in order to be able to deliver the bandwidth that's required. So technology for fast, sustainable wireless can be achieved by, again, utilizing our symmetrical horn antennas, tapping into our twist port ecosystem. This is our adapters that you know, make our antennas vendor neutral, right? So, you know, if you're using Cambium, if you're using Mimosa, if you're using Microtech, or you're using Ubiquiti, we have adapters that allow you to interface those radios into our horn antennas. And with this technology, when you utilize both of these parts, you get that massive scalability that I keep talking about and everybody is requiring, again, in order to deliver you know, fast, sustainable wireless to all their customers. So if we look at increasing the throughput with horns, you know, there's a lot of things that just the horn antennas themselves start to negate, like the need for GPS synchronization, right? So this is not to say don't use it, but there's a lot of users out there that have radios today that don't have GPS synchronization, right? So those radios now become, you know, way more usable, and you know, by using horn antennas, you have the ability to deliver more throughput with those older radios as well. So you don't need to migrate necessarily to a GPS synchronization platform if you use horn. So therefore, the ROI for the existing equipment you've purchased now gets extended because it can last longer and, you know, help deliver more throughput until you're ready to make that jump. No wide channels, right? So there's no need to jump to these, you know, 40, 60, 80, and even, you know, people are talking about 100 megahertz channels, right? These wider channels, again, are being offered and introduced in order to deliver more throughput, right? But it's quite simple. You go with a wider channel, yeah, you get more speed, but the fact is, if you used an antenna that was more efficient in spectrum, you wouldn't need 80 megahertz of channel. And in most cases, what people find when they use our horn antennas is that they usually go from what was a 40 megahertz channel on a traditional sector to just a 20 megahertz channel now on a horn, because you're able to deliver much higher, you know, much higher MCS rates through horn. So therefore, you're using that 20 megahertz more efficiently, you're delivering more throughput, and you're utilizing it to its maximum potential where you don't have to go to these wider channels. And this is actually another side effect of when we say more channels are available, is that typically you may be overusing 20, 40, or 80 megahertz overall on your tower in order to deliver the speeds you are, where when you put horns, you can actually reutilize, you can take some of that spectrum back and use it on an individual AP in order to be able to, again, deliver more throughput. So basically, all this stuff comes at practically no extra cost, right? So you just buy our antennas with the adapter and you're good to go. So it's quite simple. We're approaching the end of the webinar. So a few things I just wanted to mention, right? We have a pretty active forum. It's rfelab.com. So we're asking users to come join the community. It's a great place to post questions, find answers. There's a lot of WISPs out there that, you know, may have had the same problems you had with spectrum or colocation and what have you. So it's a great resource to you to go ahead and find out how to deal with some of the issues that you may be having. And then there's our YouTube channel, which is by far my favorite place to go for information. So we have tons and tons of webinars, customer interviews, customer visits, customer experiences. It's a great place to go and find a WISP that's dealing with the problem that you're dealing with in an area very similar to where you might be operating in, and find out how they utilize our technology in order to help them combat these problems of noise and deliver more throughput and better connections to their customers. So go to youtube.com/rfelements and check out the tons of videos that we have, again, on customer experiences, product unveilings, and all sorts of other useful information there. And then just stay tuned, right? You could always visit our website, rfelements.com. There's a lot of great information. Again, our forum is rfelab.com. And then social media. We're all over the place, whether it's YouTube, Facebook, G+, LinkedIn, Twitter, you name it, we're there. A great way to get in touch with us, ask us questions, ask other customers, which is quite frankly more important, right? You want to hear from WISPs more than you want to hear from us probably. But yeah, just involve yourself and talk to WISPs out there and find out what they're doing. So at this point, the webinar, I'm done with the webinar. So I hope we have some questions. I'll be happy to take them. If you have any questions that just popped into your head, please go ahead and type it in that little chat window, and we'll get to all of them.
Yes, we got a question. One question is, will you be offering an adapter solution to change out existing parabolic arrays into the twist port adapter application?
I'm not quite sure I understand that question, right? So we have a twist port ecosystem, right? So there's a number of twist port adapters that you can use, again, with many different vendors, from Ubiquiti to Mimosa to Cambium to Microtech and stuff like that. So if you were to, let's say, buy a symmetrical horn antenna for point to multipoint on your tower, right, and you're using, let's say, at the moment, Ubiquiti Prism radios, right? If at some point you want to change to maybe Cambium EPMP 2000 or some other radio system, the antenna stays. You just basically take that radio and adapter off. You get the EPMP 2000 adapter, for example, and then you just twist it on. So again, the antennas themselves are not made for specific radios, right? They work with any adapter, and the same thing goes for those radio adapters. For instance, you may have been using, again, we'll just say a Prism radio with a Prism adapter on a horn, and you may want to use that radio for, let's say, our Ultra Dish, which is our parabolic point-to-point antenna. You simply just take that radio off and you slip it in. You don't need a different adapter for a different antenna. Basically, if our antennas have a twist port on it, all our twist port adapters work on all those twist port radios, and therefore you don't require another antenna or another adapter. I hope that answers it. If not, please follow up.
Sounds good. Another question we have is, how far apart do antennas need to be when co-located?
Yeah, sure. Great question. It's asked often. So I'll start with the physics answer, right? Horn antennas are great. They have great co-location capabilities. They have no side lobes. So they have all these great benefits that are inherent to the type of antenna they are. But in the end, it's an antenna just like any other antenna, which means that the more space you give it, the better, right? The benefit of our antennas, because isolation is so high, front to back is so good, the absence of side lobes, you can mount these much closer together than you can traditional sectors, right? So in most cases, people just mount them about a foot apart, right? Again, if you go on social media, you go on Facebook, you can go to our RF English page or WISP pics. There's tons and tons of pictures that you can see for yourself how close they are. They are extremely close. The typical rule of thumb is at least a foot. But again, if you have 5 feet to use, go ahead and use it, right? So don't necessarily stack them from the get-go, but start closing that gap and getting them closer and closer together as you need to, right? So maybe not starting with the max, the closest space, start with the maximum that you have, and then add a third one in the middle where now they're 2.5 feet apart, so on and so forth. But 1 foot is pretty much the standard for the closest you usually can get with our horn antennas.
All right, questions are coming along. Another question is, are you recommending we use 30-degree horns for P2P links?
No, that wasn't, I know that original question was about a point-to-point, right? So I was speaking in general about the antennas and how our twist port ecosystem works, right? So the symmetrical horn antennas were designed for point to multi-point. They're your sector replacement. Now, with that said, the beam pattern is basically 30 degrees wide at the -6, and it's roughly like 20 or 21 degrees wide at the -3 beam angle. So if the links are short enough, you could. There's no reason why you can't. I mean, when it comes to antennas, the antenna doesn't care what you use it for, right? It's just a matter of whether the link budget works or not, right? There's a lot of debate on whether, well, the 30-degree horn is just too wide for a point-to-point. You need these more narrow main beams and stuff like that to do point-to-points, which is slightly true, but not always true, because if you actually look at the width of the side lobes on parabolic dish antennas, they're often way wider, way more wider than a 30-degree horn is with no side lobe. So for short links, a couple miles, you can use a 30-degree horn for a point-to-point, but that's not what the main design was. If you want a horn in point-to-point, you have to use our ultra horn. Our ultra horn is our 24 dB point-to-point horn antenna, which, at the same time, people are utilizing them for point to multi-point as well, for really narrow beam angles, for, again, just trying to pick up, clusters of customers on very narrow azimuths and stuff like that. So again, you can use it for what you want. The absence of side lobes make them highly usable for point to point or point to multi-point, but typically you need a little bit more gain because point to points are going further distances. So play with them, try it.
Okay, another question. What kind of loss can one expect from using horns with a pigtail versus a twist port adapter?
Yeah, well, so the loss that you'll get with our, let's say, our carrier class horns, which are basically the horns we've just been talking about, but instead of having a twist port adapter to accept these smaller form factor connectorized radios, they have end connectors built into them. So the loss really depends on the quality of the cable that you use, right? So I would say that just the end connector interface, that's on there is perhaps 1 dB. If you use a high quality LMR cable that has low loss and it's not too long, you're looking at potentially, 1 more dB, right? It's really not much more than what you're dealing with right now with traditional sectors that have, again, these really skinny LMR pigtails with right angle connectors and stuff like that. So it's probably a little bit more efficient because there's hopefully no right angle connectors. But I would say, probably about 2 dB for our connectorized ones. And again, it's not because of the antenna, it's about the connection interface, which is, again, using LMR pigtails to connect your radio to it. So if there's a twist port adapter available for the radio you want to use, you should use that. That's what they were designed for.
Great. I've used RFE 30s and 60s, but I'm finding substantially less throughput and signal levels from the 60s. Why?
Mm-hmm. Okay, well, I mean, there's a lot of reasons why that can happen. It's hard to answer that without, but I'm just going to venture to say it's probably because of the gain difference, right? So, as a user, you need to understand the different gain, and I'm not saying you don't, right? But users need to understand that all these sectors aren't the same gain, just at different widths, right? So the wider horns have much less gain. So for an example, a 90-degree horn has only about 10.5 to 11 dB of gain. So it's quite low for a sector. So a 90-degree horn is typically used for much smaller distances, right? 1 to 2 miles or less, right? Not going beyond that. If you look at a 30-degree horn, it's the highest gain because it's the most focused, right? And it's roughly about 18.5 dB. So you will get the most distance out of that antenna. The 60-degree horn, I believe, is roughly about 15 dB gain, right, at 60 degrees. So right there, you're looking at a 3 to 4 dB less gain than the 30-degree horn. So, if you're utilizing that 60-degree horn for, trying to cover the same distances you are with a 30, you're certainly going to see less performance because it doesn't have enough antenna gain for those longer distances. What I suggest is you, again, go to our website, rfelements.com, and check out our link calculator. It's a very simple tool to use. You drop in you pick from the list which horn you want. You set your TX power, right, to be within EIRP limits. And then there's a little slider there that allows you to check the different MCS levels from, so you can set it to MCS 7, which is 64 QAM, or MCS 9, which is 256 QAM, the highest modulation rate for most radios today. And it'll tell you how far that radio can go based on the CPE that you're using. So again, my assumption is maybe you're using that horn for greater distances and it's really made to cover based on, again, the gain of that antenna.
Okay, just a couple more questions.
Yeah, no problem.
Is there a way to use one of your horn antennas on a Cambium 450 AP?
Yeah, definitely. So again, I mentioned it, I think, a couple of questions ago. So when it comes to our symmetrical horn antennas, we have two different types, right? We have our twist port horn, and this is that waveguide fed near zero loss thing that has all these different adapters for different connectorized radios. They're typically small form factor radios like the Prism radio, Rocket M5, the C5C from Mimosa, or the EPMP 1000 or EPMP 2000 for Cambium, right? So we have unique adapters for a bunch of different radio platforms. Again, on our website, if you go to the twist port section, you can see which ones are supported. Now, for all other radios that we do not have a twist port adapter for, we have our carrier class horn. Again, this horn antenna, the carrier class horn, has the same exact RF properties as the twist port. The difference is it has two end connectors built in that allow you to, again, use a pigtail jumper from the antenna to any other 5 gigahertz radio that we don't have an adapter for. And the PMP 450 is a perfect example of one of those.
Okay, great. When setting down tilt on the horns, are you measuring the angle off of the face or at a different location on the horn?
Okay, so again, I think I'm understanding. So are you asking what's the proper way to calculate or measure down tilt as you're actually tilting it? What most people do is they actually use their cell phone, right? So there's some pretty good angle sensors that you can download from iTunes or the Google Play. That's pretty accurate within degrees, right? So they usually hold their cell phone up against the flat radome of the front of the antenna, and you just tilt it, and it'll tell you 1, 2, 3, 4, 5 degrees, and then you lock it in, right? So that's physically the best way I know of, again, measuring, do I have the 3 degrees down tilt I need or not? If you're asking, how do I know how much down tilt to use? The answer to that is, again, use our link calculator, right? So if you go to rfelements.com and you go to our link calculator, again, the same calculator where you can pick the horn, you can set your output power and MCS rates, also has a down tilt calculator. So you can put your furthest customer, let's say it's 3 or 4 or 6 miles, whatever it may be, drop it on the map, and then you can adjust the slider to 1, 2, 3, 4 degrees and keep going up, and you can watch the expected signal drop, and then you can start playing with that. You can see how much down tilt you can use before that furthest customer starts to fall off or starts to receive too low of a signal, and that's how you know how much down tilt you can use, right? In most cases, people don't use much. It's usually 1, 2, maybe 3 degrees. The only time we go kind of beyond that is when we're using higher gain horns than we really need for the distance we want to cover, or there's a specific cluster of customers you just want to point this horn at and nothing else, right? So in most cases, it's only a couple to a few degrees of down tilt is kind of standard, or none at all. And then it's aggressive down tilt, 10 plus degrees, because again, you're trying to limit the distance of a specific horn to a specific area. And the link calculator can help you see all that stuff. And you can always reach out to us if you have any problems. On the link calculator page, there's 2 how to use videos. I suggest you watch those. They'll take you through the step-by-step of how all the knobs work and how things are affected and kind of explain it. If that's not clear enough, you can just reach out to us and I'd be happy to help you personally.
So here's another question. Not sure if it'll be a simple answer, but I'll go ahead and ask it.
Yeah.
With 60s installed at many sites, I am seeing better upload speeds from client to tower than downloaded from tower to client. Is this most likely colocation interference coming into play?
Yeah, again, that's hard to answer without knowing the environment more. It could be. You know, again, it really depends on the distances you're covering and what type of CPEs you're using. You know, in high noise environments today, let's say absent of our antenna technology, people are combating noise with gain, right? So you'll often see people using really high gain parabolic dish antennas as CPEs for distances that are really too short for that kind of gain, right? And because of that, you usually have a large mismatch in receiver sensitivity, because that large parabolic dish has much higher receive gain because of the fixed gain of the antenna plus the inherent receive sensitivity of the radio, that you can get an imbalance in upload and download. So part of it, you know, could be noise. Part of it could be maybe this mismatch in antenna types. I don't know where you fall into this thing, but it could be. It could be. And you know, again, if you want to contact me personally, you can offline through Facebook or info@rfelements.com, and I'll be happy to talk to you directly and try and sort out this issue and look at it in more detail.
Great. Another question that just came in. Will there be Twistport products for ePMP 3000 series?
It's too early to know. I personally don't think so. The radio is quite large. I don't know if you've personally seen it. So really, typically the radios that we utilize or that we'll make adapters for are a smaller connectorized form factor, typically light as well, or lighter. The ePMP 2000 is like the largest form factor we've ever made a twist port for. The ePMP 3000, if you haven't seen it, is almost twice as long and all metal, so it's really heavy. So I don't think it's a good candidate for a twist port adapter, but you'll always have the ability to utilize our carrier class horns with them if you still want to use our horn antenna technology with ePMP 3000. So it's a little early. We'll see.
Great, and I think that's pretty much all the questions. There are a few questions that I'll send to you directly that that you can answer offline with the customers.
Yeah, that'd be great.
Yep, and as always, like Tassos mentioned, you can always get a hold of him through Facebook or through email, and you can always contact us at StreetWave, and we'll be able to happily answer your questions. Is there anything else that you wanted to add, Tassos, before we leave?
No, that's it. Thanks everybody for joining. And like I said, I look forward to talking to any of you if you have any further questions. Thanks.
Thank you. Bye.
Bye.